Bismillahirrahmanirrahim. Hi, hello everybody. Uh, let's continue on our class today. Okay. Today, the topic, a new topic that we will be covered. Chapter number 3 about first law of thermodynamics. So, before I start the new chapter of this course, I like to make the acknowledgement. Thank you very much to my cliques members in UITM Shah Alam, College of Engineering in Mechanical Engineering, Dr. Idris Saad, also Dr. Al Hassan Salami, and Dr. No Afiffah. Because of their efforts of doing to produce these slides or of the course of thermodynamics. So as usually, this is a thermodynamics. The code is MEC451 and it is also as same as MEM462. Okay. Okay. Uh, First of all, in this topic, I would like uh, you guys to know that what actually you have or you able to know about this topic. Firstly, the objective of this chapter number 3, okay, uh, student or you or guys, you must be able or can able to be introduce the concept of energy and define its various form. Okay, that is objective number 1. What you have to know. Number 2. Also, the objective. I will discuss the nature of the internal energy. Uh, and then we'll define the concept of heat and the terminology associated with the energy transfer heat system. The fourth objective is the concept of works. That means in this chapter, students should able to know the concept of works, including electrical works and several works for mechanical works. Okay. And then from there you will be introduced to first law of the thermodynamics, energy balance and mechanism of energy transfer to or form a system. So this first we will look on the closed system, uh, and then second part, okay, the first part of this chapter number 3, we'll look on the closed system, and the second part we will look, inshallah, on the open system, or another is called as a control surface system. Okay, that is the objective that you have to know. So hopefully student, you will know what you are learning about, and also you will be focused on this chapter. Let's look on the course. Okay.
Assalamualaikum warahmatullahi wabarakatuh. Hello everybody. Okay, today class is about chapter number 3. So we continue with the online lecture. So what you all have learned is on chapter 1 and chapter number 2. So based on the chapter number 1, you also have seen on the first law of thermodynamics. Okay, here in this chapter, what I know you already learned about number 1, And you also already learned about number two, and also a little bit on number three. Okay, maybe on number three, I will discuss more detail after this. You also have learned or seen number four. Um, that's mean based on number four, it is about the first law of thermodynamics, but we focus on the closed system. Okay, then okay, we continue go to first law based on number three. Okay, actually, what I want to tell you here is about the work that can we calculate. Last time, previously, I only told you about work is based on W is equals to integrate PDV. That is the work for the moving cylinder. Beside of that, you also can calculate based on the work found in the electrical work. So based on the electrical work, the work that we can calculate is based on this formula, and the power that we can also calculate based on this formula, where the power is equals to voltage time current. So from here, the work we can find use the concept of integrate V I dt. Okay, this is the formula of the work based on electrical power. Number two, the work based on the mechanical form of work. So this is the mechanical form where I have already told you about this analysis based on the moving part. Okay, and another work is come from the shaft work. Okay, the shaft work. If you want to find the work from the shaft, the formula can be used is work is equal to 2 pi and T, where T is a torque that may be given from you for you in the question or in the case. So this is how the situations, the simulation of torque occur around us. Okay, we have tangents, rotations, the force. So the torque is force times with distance. So using this formula, you can have a shaft work according to the formula, and the unit is kilojoule. And also from the work, we also can get a power of work. That means work is equal to 2 pi n dot top, where if you see W have a 1 dot upper of it letter head, that means this is defined as a power. Okay, we go to the spring work. Another element of work can be calculated is spring work. Spring work also if we use the formula work is equal to F force times ds. ds is the distance of what we call the point distance of where the spring is moving, and F can be calculated by K times S. Okay, where K is the constant, spring constant. Actually, given in the equations. Sorry, given in the question. And when we substitute and integrate it, and we get work is equals to, this is formula for work based on spring. Okay, so okay, this is example where the case of spring has been introduced to thermodynamics. Okay,
Moving boundary work. Okay, this actually one of the mechanical mechanisms that can produce work. Actually, this is deals with the expansions of compression of gas. in a piston cylinder device. So during this process, what happened? The part of a boundary, that means the interface of the piston, move back and forth. So therefore, the expansion and compressions works is often called moving boundary works, or another name is simply boundary works. Okay, so the capital W is the symbols that we use to calculate this work. So when you want to analyze these moving boundary works for the Cauchy equation equilibrium process, the process during which the system remain in equilibrium at all times. Okay, let's see the figures at the right. So this is a piston cylinder device. Okay, okay, this is a piston cylinder device. So in this, it shows that the gas, okay, that have in this cylinder, when we heat or when we cool the gas, the boundary will be expand or compress. So to find the work that uh, that have in this piston cylinder device, uh, so we can do or we can show these expressions in the in the mathematic model. So to find this work, so we differential work done by this process. So we take the force, that means the force that have in the piston at the piston, time the ds, that is the distance uh, of the movement. Okay, so it will equal with uh, pa time ds. Okay, because the pressure, the formula for pressure is p is equals to f over a. Okay, so from here we can simplify the equations. P is uh, P equal P times dV, because dV is the volume of this system, whereas the volume is area A time the ds, distance. Okay, this area time ds will get the volume. So from here, the total boundary work done during the entire process as the piston move is WB is equals to integrate state 1 to state 2 P dV. This is the general equations that can we use to calculate uh, in case of the moving boundary work. And the unit we use here is kilojoule or joule. Okay, this is how we express the moving boundary works in the graph of pressure versus volume. Okay, this is a process that happened from state number one to state number two. So from here, um, the total area under the process 1, 2 is obtained by adding this differential area. So the area is integrate dA. So dA P dV. Okay, we know that the area is dV times P pressure. So the equation above reveals that the area under the process curve of the PV diagram is equals in magnitude to the work done during the quasi-equilibrium expansions. or compression process of a closed system. So a gas that follows several different paths as it expands from state 1 to state 2. So during actual expansion and compression processes of gases in either processes, pressure and volume of the process path often related by PV powered by N is equal to C. So where N and C are constant. So this is called a polytropic process, where N is known as a polytropic index. Okay, powered by N is a polytropic index. So in general, each path with different value of N will have a different area of underneath it. Okay, this is the mathematic expression. So when N is different value, so we will have the process path at different curve. Okay. Actually, this boundary work can be divided into 5 processes. So in thermodynamics, we will cover only in these 5 processes. Okay, that means a student, you have to remember all these 5 processes that will happen in thermodynamics. Okay, we look on the first one. The first one is called as isochloric process, where this isochloric process is for the constant volume process. So when you look at the PV diagram, okay, when the volume is constant, what happen? The graph will be vertical line. Okay, so since the dV or the volume is zero and the volume does not change during the process, then the boundary works we can express in mathematics as integrate PdV as zero. So for ideal process, PVN equal to zero, then N is equal to infinity. So when you have these situations of process, you can use the ideal gas equations PV MRT, and you can conclude that these equations, or you can assume as a constant volume process, the mathematics can be used is P1 over T1 is equals to P2 over T2. Okay, that is a for constant volume process. Number two is a boundary work for the constant pressure process. When for the constant pressure process, this process actually called as a isobaric process, and the diagram that can show this process for pressure versus volume is a graph, uh, horizontal graph. Okay, a straight line of horizontal graph. Since the pressure is constant, that means pressure does not change during the process. So we we use the boundary work equations. W work integrate PdV. So from here, only the volume, okay, the volume change. So we can put for the this dV volume V2 minus V1, or WV, capital WV is work is equal MP delta V. So for the ideal process of ideal gas, PV powered by N equal to C, then N is equal to 0. Okay, or when we use these ideal gas equations, PV MRT, then what happened? We can you can simplify this equation become V1 or P T1 equals to P2 V2 over T2. Okay, that is for isobaric process. Number 3 is about constant temperature process. Okay, this process called as an isothermal process. And the sketch of the system at the PV diagram is like shown. Okay. Okay. So this is very different from the other two process because isothermal process, the line is a curved line. Okay. The first one and the second one is the straight line, horizontal and vertical. But isothermal process is a curved line. So using the boundary work equations, PdV, where P, okay, where P pressure is for the ideal gas of constant temperature, where T is constant, then PV is equal to MRT equal to C, okay, because T is constant. So we can you can simplify this equation become P equals to V over C. So in these equations, work equals to integrate PdV. So for P, we use C over V. We put C over V. Then C is constant. We take out from the integration. And then what happen? You only integrate dV over V. So this is mathematics. How you integrate this dV over V. So then it will come out the equation P1 V1 ln V2 over V1. So I can also use PV equals to MRT. So it will become also MRT ln V2 over V1. So for the ideal process is PV powered by N equal to C. Then for the ideal gas, then N is equal to 1. So when N equal to 1, using ideal gas equations, we can simplify or we get the N equations of P1 V1 equals to P2 V2. Okay, or other ways. Okay, like this. Okay, process number 4 is adiabatic process. Adiabatic process is one that occurs without transfer of heat or mass between the thermodynamic system of its surroundings. So energy is transferred only as work. So this process also known as the isentropic process, where S one or S at state 1 is equals to S at state 2. Okay, when we look at PV diagram, the isotropic, the adiabatic process have a curved line, okay, like the isothermal process. But different value of N will give a different curve. Okay, so um, if you look adiabatic versus isothermal process, the isothermal process is one in which the temperature is constant. That means heat can be gained or lost in order to maintain at a constant temperature. But in adiabatic process is one in which there is no heat exchange between a system or its surrounding. Okay, please remember this statement. Okay, please and this is a thermodynamic knowledge. So for the adiabatic process, there is no heat exchange between the system and its surrounding. So it does not matter whether the temperature of the system is constant or not. So to do describe in the mathematics using the boundary moving work equations. So we integrate PDV. From PDV, we know that PV equals power by N for the adiabatic or isentropic. where n equal to k. Okay, remember k is the ratio of Cp over Cv. Okay, then PV powered by k equal to c. So you can rearrange these equations. Then in this equation, when P, you can put C over V powered by K, replacement P. So integrate these equations will give the last equations of work that will be used or calculate in the adiabatic process. This is the equation will be used. Okay, and then for the ideal gas, state 1 to state 2, PV powered by K equal to C. So C is constant, so we can put to same equations at the left and right. So it will become, or it will be simplified like this. Okay. Okay, and the last one of the process that have in the moving boundary work is called polytropic process. So the polytropic process, the law that have in this curve line is PV n equal to C. Okay, that is a law. So that means the polytropic process is a thermodynamic process that obey the relationship. That means what I said, a law is the relationship that means used in this process. So where P is pressure, V is specific volume, N is the polytropic index, okay, and C is constant. So from here, using boundary work equations, um, it will give PdV. So P we can take from the relationship. So it will become Cv powered by negative n dV. So you integrate these equations, then it will become like this and simplify. Then lastly, it will give this answer for formula work for the polytropic process. Okay, and if you look the diagram, PV diagram, the process for the path has also have a curved line. So for these five processes, please remember uh, process number one, number two is a straight line. That means for isobaric and isochloric is a straight line. But for others three processes, that means isothermal, adiabatics, and polytropic, the graph line is a curved line. Okay, it's a curved line. So that is a description of in detail about the process that will have in the thermodynamics. Next, we look on the sorry. Okay, this is a summary of the boundary words. So what I have told you uh, about the five processes, this is a summary. Okay, so the process you can look here, isochloric, the formula that can be used, isobaric, isothermal, polytropic, and isentropic. Eh? This all the formula that we use. Okay, maybe this is the theoretical that you have to remember and understand. So to make it more understand. So I will show you on the question and solution, or on the examples or question and solution. Okay.
This is energy balance for closed system. Okay, this actually the this title actually means the first law of thermodynamics based on closed system, where we have learned in chapter number 1. I have defined that when you see the question based on the closed system, we neglect kinetic energy and also potential energy, and the first law equations will become NFEE. That means non-flow energy equation, and this equation is based on Q minus W equals to delta U only. Okay, and this all the a simple problem that can you make an exercise. This is a practical problem. Okay, this one we will see in next lecture. Okay, so that's all for today for the lecture, and after this I will give you some cases, and then we discuss from there. Okay, thank you very much.
After you have learned about the theoreticals, and also you have seen the work mechanisms that involve with the heat and work energy. So now let's discuss, or I will show you some of the examples about the problems that can deal with the first law of thermodynamics for the closed system. Okay, so I would like to introduce the question and solutions that I take it from the YouTube channels, and it will help you as examples to solve the problem of first law of thermodynamics. So let's see from these professors. Okay, professors from the first one. Okay, the first one is from Department of Chemical and Biological Engineer, University of Colorado, Boulder, Professor Dr. John Falconer. Okay, so we can learn. Okay, thank you very much, Professor, because your slide, your video, YouTube, you sharing with us, and then we can see or learn something from your discussions. Okay, this is number one. Thank you very much. And also the second one, that's from Professor Jayant K. Singh, Department of Chemical Engineering, Institute, Indian Institute of Technologies, Kanpur. Okay, so thank you very much, Professors Jayant, because sharing your discussions about the problems and solutions regarding to the chapter 3, first law of thermodynamics. Okay, let's go to these two professors discussions.
We're going to apply the first law to two closed systems and then compare the final results. One's a constant pressure system, piston and cylinder. The pressure is 0.5 megapascals. The other is a fixed volume cylinder. They both contain 1 mole, and they're starting at the same temperature, same pressure. So they're starting at the same volume. We want to know what's the final temperature and the final pressure in each container after we add 8.5 kilojoules of heat to each system. And so the first is the container A, the constant pressure system. So just so we have a representation, what we're looking at is a piston with constant weight, and we're adding heat. We're starting at 350 Kelvin, 0.5 megapascals, and the heat we're adding is 8,500 joules. We'll work everything in joules. And so the first law, closed system, change internal energy is heat plus work, and the change in internal energy is CV delta T for an ideal gas. Independent of the type of process, that's what is equal to Q, of course, is a fixed number. Work is minus pressure times the volume change. And since we're dealing with ideal gas, we can take advantage of the ideal gas. We're at constant pressure, so minus delta P dV is the same as delta PV because pressure is constant. Because this is an ideal gas, working with 1 mole, this is the same as delta RT, which R is constant, so that's R delta T. So I can make that substitution into the first law, and I can rearrange. So minus R delta T. So let me bring this to the other side. Now CV plus R is equal to CP for an ideal gas. So now we can find the final temperature. Let me substitute the values. So keep in mind we're working with 1 mole. So if you like, we could, CV would have number of moles in front of it, which is 1. So the units cancel, and I can solve this equation for the final temperature. So the final temperature, and of course the final pressure is the same as the initial pressure. So let's do the same calculation over here for the constant volume system. And constant volume means there's no work, so delta U is Q plus W, that's 0. Delta U is the same as before. CV is CP minus R, so CP is 31, R in the correct units, so we have everything in joules per mole Kelvin. T2 minus T1 equals Q. So let's substitute in the values. CP is 31, R 8.314, both units joules per mole Kelvin. T2 minus 350 equals 8,500 joules. So I can rearrange and solve for the temperature, end up with the final temperature of 725 Kelvin. And then I can use the ideal gas law. Because volume's constant, I can get the final pressure is R T1 over P1. Well, R's cancel. I can rearrange that P2 is equal to P1, T2 over T1, 0.5 megapascals, 725 over 350, P2, 1.03 megapascals. I'll write that significant figures 1.0 megapascals. So the pressure essentially doubled. You'll notice the temperature is significantly higher for the constant volume process, about 100 degrees higher, because in the constant pressure process here, some of the energy, some of the heat that was added went into work, which was removed from the system. The rest went to raising the temperature, increasing internal energy. In the constant volume system, all the energy, all the heat added went into raising the temperature, increasing internal energy, and therefore the temperature is higher.
Welcome to this tutorial. Myself Manish Maurya. I am a TA of this course. In this tutorial, I will take you through few examples based on energy balance for closed system and moving boundary work. So let's start with the first question. A piston cylinder device contains 0.15 kg of air initially at 2 megapascal and 350 degree centigrade. The air is first expanded isothermally to 500 kilopascal, then compressed polytropically with a polytropic exponent of 1.2 to the initial pressure, and finally compressed at the constant pressure to the initial state. Determine the boundary work for each process and the net work of the cycle. So here we assume air as the system, and this piston will compress this air polytropically, and this air will expand isothermally as well. So if you see whole process on a PV diagram, so from state 1 to state 2, this gas expands isothermally. Then from 2 to 3, it compressed polytropically to initial pressure, and then finally it compressed at constant pressure to the initial state. So we have to determine boundary work for each process. First we do calculation for isothermal expansion. So work in isothermal expansion is WB from 1 to 2 will be P1 V1 ln of V2 upon V1. Okay. Since here we don't know V2 and V1, we need to find this initial and final volume of air. So from the ideal gas assumption, we calculate initial volume like mRT upon P1. So mass of air is 0.15 kg. Gas constant can be taken from this table, which is 0.2870 kilojoule per kg into Kelvin, and temperature is 350 plus 273 Kelvin divided by total pressure, which is 2000 kilopascal. So this gives us V1 equal to 0.01341 meter cube. Now we need to know value of V2. So similarly we can calculate V2 equal to mR T upon P2. Since this is an isothermal expansion, so temperature will be the same. So value of m is 0.15 kg. Gas constant is 0.287 kilojoule per kg Kelvin, and temperature is 350 plus 273. And total pressure is 500 kilopascal. So this gives us V2 equal to 0.05364 meter cube. Now putting these values in the ideal gas work expression, P1 V1 ln of V2 upon V1. So P1 is 2000 kilopascal, V1 is 0.01341 meter cube ln 0.05364 meter cube upon 0.01341. So this gives total work in isothermal expansion 37.18 kilojoule. Now we have to calculate work in polytropic compression. So in this polytropic compression work will be from the state 2 to the state 3 equal to P3 V3 minus P2 V2 divided by 1 minus N. Since we don't know information about state 3, so we need to find this P3 and V3. So this can be obtained from equation of state for polytropic process. So P2 V2 to the power n equal to P3 V3 to the power n. So we know P2 is 500 kilopascal, V2 is 0.05364 meter cube to the power 1.2. This polytropic exponent is given to us. And P3, it is said that polytropic compression is done to the initial pressure. So that means P3 equal to P1, which is 2000 kilopascal. So putting this value here, and V3 that we need to calculate to the power 1.2. So from here we get V3 equal to 0.0169 meter cube. So after plugging these value into this expression, we get W223 equal to 2000 kilopascal into 0.01690 meter cube minus 500 kilopascal into 0.05364 meter cube divided by 1 minus 1.2. So this gives us minus 34.86 kilojoule. Now finally we need to calculate work done for isobaric process, which is from the state 3 to the state first. So this will be P3 V1 minus V3, which is equal to 2000 kilopascal into 0.01341 minus 0.01690 meter cube. So this gives minus 6.97 kilojoule. Finally, we have to calculate the net work for the whole process. So the net work of the whole process will be the sum of the total work in each process. So W net will be W from the state 1 to state 2 plus work done from the state 2 to state 3 plus W from the state 3 to state 1. So this gives 37.18 plus minus 34.86 plus minus 6.97 kilojoule, which is nothing but minus 4.65 kilojoule. So this is the total work in a complete cycle. So moving to the next question. In this question, 1.5 kg of water that is initially present at 1 megapascal and 30% quality occupies a spring loaded piston cylinder device. This device is now cooled until the water is saturated liquid at 100 degrees centigrade. Calculate the total work produced during this process in kilojoule. So it is said that initially cylinder is filled with water vapor mixture having quality of 30%. So if you see this process on a PV diagram, so initial state would be somewhere here because it is a mixture of water and vapor. So this state will be here, and now it is further cooled until that water is saturated. So it will cool down to this state, state 2, because this is a saturated liquid. So we have to calculate total work produced during this process, and here we assume that the process is quasi equilibrium. Okay, so the total work produced in this process would be area under this line. So W total will be area of this shaded region. Shaded part. So if we divide this region into part, so this will be the area of this triangle A, B, C, D, E plus area of this rectangle. So this will be the area of B, C, D, E plus area of the triangle ABE. Okay, so area BCDE will be nothing but, if we see pressure at this state will be P1 and pressure at this state will be P2. So the total area of BCDE will be P2 into change in total volume. So change in the specific volume into mass plus area of this triangle, which is 1 by 2 AE into BE. So AE is nothing but P1 minus P2 and BE is total change in volume. So mass times change in specific volume. So this gives an expression for total work during this process. Okay, so this is our first expression. Okay. So now we need to know the value of these variables P1, P2, V1 and V2. Since initially we know P1 equal to 1000 kilopascal, so corresponding V1 can be calculated as Vf plus x Vg minus Vf. So this value can be taken from the saturated water table corresponding to 1000 kilopascal, which is here. So after plugging this value here, we get 0.001127 plus quality we know that it is 30%, so 0.3. Vg is 0.19436 minus 0.001127. Okay, so from here we get V1 equal to 0.059097 meter cube per kg. Okay, so now we have to calculate P2 and V2 for the state 2. Since the state 2 is a saturated liquid, temperature at this state would be 100 degrees centigrade. So from the saturated water table at 100 degrees centigrade, we can calculate P2 and V2. So P2 would be 101.42 kilopascal and corresponding volume V2 equal to volume of the fluid, because it is a saturated liquid, so there is no vapor. So V2 will be nothing but 0.001043 kg per meter cube. So after putting these values in the expression 1, we get total work equal to 1000 plus 101.42 kilopascal upon 2 into mass time, which is mass is 1.5 kg, change in specific volume, which is 0.00104 minus 0.059097 meter cube. So from here we get minus 48 kilopascal meter cube, which is nothing but minus 48 kilojoule, because one kilopascal in meter cube equal to 1 kilojoule. So this is the total work in this process. So moving to the next question. A well insulated rigid tank contains 2 kg of saturated liquid vapor mixture of water at 150 kilopascal. Initially, 3/4 of the mass is in the liquid phase. An electric resistor placed in the tank is connected to a 110 volt source, and a current of 8 ampere flows through the resistor when the switch is turned on. Determine how long it will take to vaporize all the liquid in the tank. Also show the process on a TV diagram with respect to saturation lines. So here we consider vapor liquid mixture as a system, and this is the boundary of the system, and this is a closed system since there is no mass crossing the boundary, and it is given that 3/4 of the mass is in liquid phase. That means quality of this mixture is 25%, which is 0.25. Okay, so it is desired to determine how long it will take to vaporize all the liquid in the tank. Since it is given that tank is rigid, okay, that means volume is not going to change during the process. So if you see the whole process on a TV diagram, so initially it is a mixture of liquid and vapor with a quality of 0.25. The initial state would be here. Now it is heated, and it is heated such that all the liquid is in vapor state. So now this is our state 2 and this is our state first, and it is occurring at constant volume since it is a closed rigid tank. Now further we need to determine the time it takes to vaporize all the liquid. Since it is a closed system, so energy balance on the closed system will be total energy in minus total energy out equal to change in total energy of the system. Since this tank is well insulated, so there is no energy coming out of the system. Only energy in will be here equal to change in total energy of the system. Since system is stationary, okay, so delta K and delta P will be 0. Delta E system is nothing but change in internal energy K plus P. So these parts are 0. Only internal energy of the system will change, which is mass times change in specific internal energy. And energy in is nothing but energy coming out from this resistor, which is V times current into delta T. So the total energy during this interval will be Vi delta T. So we have to find this delta T. So for that we need to know U2 and U1, and we know V and I. So initially it is given that initial pressure is 150 kilopascal. So we know initial pressure is 150 kilopascal. So corresponding Internal energy can be calculated as U1 equal to U of the fluid plus X time U Fg. Okay, so it is given here UF is here, this one, and UFG is nothing but UG minus UF. So UFG is this one. So U1 will be 466.97 plus quality, which is given as 0.25, and into UFG, which is 2052.3. So this gives us 980.03 kilojoule per kg, and corresponding specific volume can also be calculated as V1 equal to Vf plus X time Vg minus Vf. So Vf is given 0.001053, which is here in this table, this point and this point. So 0.001053 plus 0.25 into 1.1594 minus 0.001053. Okay, so this gives us 0.20905 meter cube per kg. Okay, so now we need to know internal energy and specific volume at state 2. So since it is given that volume is not changing, so V2 will be equal to V1, okay, which is 0.29065 meter cube per kg. Okay, we have to calculate internal energy at this state. Okay, so internal energy can be calculated at this given specific volume from this table. We don't have internal energy corresponds to this specific volume exactly, so we have to interpolate the internal energy between these two volumes. So after interpolating internal energy in between these two values, we get 2569.73 kilojoule per kg. So this is the internal energy at this specific volume. So after plugging these values in the energy balance, which is Vi delta T equal to mass times change in internal energy. Okay, so delta T will be equal to m U2 minus U1 upon V into I. So after putting these values, m is 2 kg, it is given, U2 is 2569.73 minus 980.03 upon 110 volt into 8 ampere. And since 1 kilojoule per second is equal to 1000 volt into ampere, so this gives total time equal to 3612.95 second, which is nothing but 60.22 minutes. So this much time it will take to vaporize all the liquid in the tank. So let's move to the next question. An ideal gas contained in a piston cylinder device undergoes an isothermal compression process, which begins with an initial pressure and volume of 100 kilopascal and 0.6 meter cube volume respectively. During the process, there is a heat transfer of 60 kilojoule from the ideal gas to the surroundings. Determine the volume and pressure at the end of the process. So here is the air compressed in this piston cylinder device. So this is the boundary of our system. Okay. So since this is a closed system, because there is no mass crossing the boundary of the system, so energy balance for this closed system will be total energy in minus total energy out equal to change in total energy of the system. Okay. So energy in will be from the work done by this piston on the cylinder. So that work in is the energy coming inside the system, and since it is losing its energy to the surrounding, so that becomes our Q out, and delta E of the system will be changing total internal energy because system is stationary. So delta Ke and delta Pe will be 0. So since this is an ideal gas, so delta U will be mCv delta T, that is T2 minus T1. Okay. So from here we get, since this is an isothermal expansion, so this will be 0 because T2 equal to T1. So from here we get W in will be equal to W out, that is total work done on the system is equal to total energy coming out of the system. So we know isothermal work done WB in is nothing but the PdV work from the step 1 to 2, which is P1 V1 ln of V1 upon V2. So this is work done during this isothermal compression. So this gives us V2 upon V1 after rearranging this exponent of minus W work in upon P1 V1. Okay. So from here we know that WB is equal to Q out. Okay. So plugging this value here, minus Q out upon P1 V1. Okay. So now since we know Q out is 60 kilojoule, so V2 upon V1 equal to, it is given in the question that energy coming out of the system is 60 kilojoule. So this is minus 60 kilojoule upon initial pressure is 100 kilopascal and volume is 0.6 meter cube. So this gives exponent to the 1 minus 1. So from here V2 will be equal to 0.3679 times V1. Okay. And V1 is 0.6 meter cube. So 0.3679 into 0.6 meter cube. So this gives V2 equal to 0.221 meter cube. So this is the final volume. We need to find the final pressure of the ideal gas as well. So that can be found from the ideal gas law. So from the ideal gas law, P1 V1 upon T1 will be equal to P2 V2 upon T2. Okay. So P2 will be P1 times V1 upon V2. Okay, because this is an isothermal process. So P1 is 100 kilopascal V1 by V2 is nothing but 1 upon 0.3679. So this gives final pressure equal to 272 kilopascal. Coming to the final question, air is contained in a piston cylinder device at 600 kilopascal and 927 degrees centigrade and occupies a volume of 0.8 meter cube. The air undergoes an isothermal process until the pressure is reduced to 300 kilopascal. The piston is now fixed in place and not allowed to move while a heat transfer process takes place until the air reaches 27 degrees centigrade. First we have to sketch the system showing the energy crossing the boundary and the PV diagram for the combined process. Second, for the combined process, determine the net amount of heat transfer in kilojoule and its direction. Assume air has constant specific heats evaluated at 300 Kelvin. So first we have to draw this sketch of this system. So initially air is contained in a piston cylinder device at 600 kilopascal. Okay, temperature is 927 degrees centigrade and volume is 0.8 meter cube. It is said that air undergoes an isothermal process until the pressure is reduced to 300 kilopascal. That means air will do some work on the piston and it will lose its pressure to 300 kilopascal. So that means it will lose its energy to the surrounding as well. It is also said that after some time piston is not allowed to move. That means after some time piston is not moving. Okay, it is constant here. So the volume of this system will not change. So this is the sketch of the system. So if we see the whole process on a PV diagram, so it is said that it is initially expand isothermally from a pressure of 600 kilopascal to a pressure of 300 kilopascal. Okay, then it is cooled at a constant volume. So let's say this state is state 1 and this is state 2, and it is cooled at its constant volume at some state. So this is our state 3. In the second part of the question it says that the net amount of heat transfer in kilojoules. So we need to determine the net amount of heat transfer. So for that, this is a closed system. So for closed system, energy balance would be like E in minus E out equal to changing energy of the whole system. Since there is no heat coming inside of this system, so that means energy in is 0. There are two things crossing the boundaries of the system, that is Q out and the work done by the system on the surrounding, which will be equal to change in total internal energy of the system, because system is stationary. So total change in internal energy of this system will be nothing but mcv delta T, T3 minus Tn. Here we assume that this air behaves as an ideal gas. So from here we get minus Q out equal to net work done by the system plus change in internal energy. Okay, so we know this is the total work done by the system. Since process undergoes an isothermal expansion from the state 1 to state 2, and then it goes an isochoric process from the state 2 to 3. So total work W B out will be W from the state 1 to state 2 plus from the state 2 to the state 3. So this is an isochoric process, so the work done will be 0 because volume is constant. The only work is done by the system is during the isothermal expansion. Okay, so isothermal expansion work for an ideal gas will be MRT ln of MRT1 ln of V2 upon V1. Okay, but for isothermal process, V2 upon V1 equal to P2 upon P1. So from here WB 1 to 2 will be MRT ln of P2 upon P1. So in this expression we don't know mass of the air initially present in the system. So from the ideal gas equation we can calculate the mass of the air P1 V1 upon RT1. Okay, so after plugging the values of P1 V1 and RT1 we get 600 kilopascal initial pressure. Volume is given that 0.8 meter cube. The value of R for air can be taken from the ideal gas table, which is 0.287. So R is 0.287 kilopascal. We have to convert this unit according to numerator units. Okay, so kilopascal into meter cube upon kg into Kelvin times temperature, which is 1200 Kelvin, since initially air is at 927 degrees centigrade. So this gives 1.394 kilogram. Okay, so total work will be 1.394 kilogram into R 0.287 kilopascal into meter cube on kg into Kelvin, and initial temperature is 1200 Kelvin into ln of P2 by P1. Okay, so 600 kilopascal to 300 kilopascal. So from here total work will be 332.8 kilojoule. Okay, so now plugging this value into the energy balance equation. So from there we get minus Q out equal to work done, which is 332.8 kilojoule, plus change in internal energy, so mCV delta T. So m is 1.394, CV of the air can be taken from this table, which is listed here, 0.718, so that can be used here, 0.718 kilojoule per kg into Kelvin, and delta T is 300 minus 1200 Kelvin. Okay, so this gives total heat coming out of the system is 568 kilojoule. So this much amount of heat will come out of the system. So here we will stop. We will meet you in the next tutorial. Thank you.